In section 6, we're going to be looking at inequalities in triangles. We're just going to be looking at things happening within one triangle, and we're going to look at those inequalities involving angles and sides. They give us a problem where they have a couple of boards, one is 8, one is 5, and they want to make a triangle to build a sandbox, and so they need to know how long the third side is, and they wonder which of these boards can be used for our third side. Now what we can look at for this is if I put two sides together, how long could that third side be in order to make a triangle? Notice that if I put those sides together, sometimes I might not have sides that are long enough to actually come together and make a triangle. So if two of the sides are too short, we're not going to get a long enough triangle. If I make them a little bit longer, there might be somewhere where those could actually meet and make a triangle. Now before we can do some of these proofs with inequalities, we have to understand the definition of an inequality. So one of the things with an inequality is if I'm comparing two numbers, say I'm comparing A and B here, and I know that A is the sum of two numbers. Notice that C, they just tell us it's a positive number. So if I have to add something to B to get A, then I know that B has to be smaller than A. Now to prove this then, we just start with, we know that C is a positive number, and if C is a positive number, notice adding B to each side, addition property there, wouldn't change the inequality. And since I'm adding 0, I can just say that this is greater than B. So that's the identity property, 0 is the identity. And we were also given that A is equal to B plus C. So what I'm going to do here is I'm going to take this B plus C from here, and I'm going to substitute in the A in my next step, so therefore I know that A is greater than B. So this is just telling us the definition of inequality. If I'm adding two things together to get another number, I know that A is bigger than either of those parts, as long as we're dealing with positive numbers. And since we're dealing with measures in geometry, all of our numbers are going to be positive because you can't have a negative angle. Now when we think about an exterior angle, remember that's the red angle here, and compare it to the green angles, remember that if I can always add these two green angles to get the exterior angle. That was the exterior angle theorem. Also notice, look at the measures of these angles. My green angles are here and the red one here. If you remember, I can add these to get that. And no matter where I move this, if I compare these numbers, each one of these numbers is less than the red number. However much I try to stretch out my green angle here, it's still going to be less than my red angle. Okay, so this leads us to our corollary here that the exterior angle is always greater than either of the interior angles. So I can be given that we can use the exterior angle theorem, which tells us that outside angle is equal to the sum of the interior angles. And then notice how this clearly fits into this property here, the comparison property. If the two parts add up to give us the whole, then either one of those parts has to be less than the whole thing. Then each one has to be less than the larger angle. In this kind of problem, we're looking at a figure that has some exterior angles and some interior angles, and we want to know which angles are less than 1. Now we want to know for sure. We can't just go by what it looks like on our picture because our picture could move a little bit, but we're looking at the relationship of the angle. So if I'm starting with angle 1, then we notice that that angle 1 is an exterior angle only for this triangle up here where we have 3 and 4 inside. So we know that angle 3 and angle 4 are less than angle 1. If we're asked which angles are less than angle 5, then we'll notice that angle 5 is an exterior angle for this whole triangle over here. And so considering that picture, angle 5, we would have these two angles, which would be angle C and angle A, or angle 3 up there. Now we don't know anything about 4 and 2 here. It does look like 4 is less than 5 or 2 is less than 5, but this is only telling us about the relationship. So I could have the same picture maybe where 5 is over here and my 4 and 2 look something like this, depending on what that is. And it doesn't really tell us anything about angles 1, 4, or 2. We only know for sure about angles 3 and angle C over here. Now we could also be asked which angles are less than angle 4, but if we look at angle 4 here, angle 4 is not an exterior angle for any of these triangles. And so we really don't know if any of these are less. There's no information or not enough information here to tell us anything about any of the other angles compared to angle 4. Now, the next theorem is looking at comparing angles and the sides opposite of them. So notice if we're looking at opposite angles here, if I compare this red angle and the side opposite, or this angle up here and the side opposite, or the green angle side opposite, notice how if I look for the smallest angle, okay, right now that's the red angle, and I look for the shortest side, notice that would also be the red one. If I look for the biggest angle, right now that's 89, and the longest side, notice that they're across from each other, and the middle ones are also across from each other. So whenever I move this, if I look for the smallest angle, it's always going to be across from the smallest side. And the largest angle will always be across from the largest side. And that's going to give us two different theorems. One of them is if we look for a longer side, I know that the angle opposite of that is larger than the side opposite of that. Or the angle opposite of the larger side is bigger than the angle opposite of the shorter side. And then that's also going to be true if we turn that around and look at it the other way. If we know where the largest angle is, or the larger angle, it's going to be across from a larger side. And one way we could use that, in this problem, the architect's looking for the corner with the largest angle to set a park bench. Now we can kind of see that from the picture, that would be here, but we shouldn't really rely on that. What we really want to look at is where is the longest side. So 175 is longer than each of these, which tells us that this angle right here between MLK and Valley Road has the largest angle. In the next problem, they're asking for the second largest angle, so we're looking for the second largest side. So 105 would be the shortest. That makes 120 the second largest side, which would mean that our angle here would be the second largest angle. In this next problem, we're asked to put the sides in order from shortest to longest. So what we want to do is look at the angles. Now to do that, we first need to find our third angle. Just remember our angles add up to 180 degrees. So if we look at 62 and 58, that gives us 120, and that means the third angle would have to be 60 degrees. So if we're wanting them in order from shortest to longest, let's look first at our smallest angle. The shortest side would be across from that. So we're looking at TV, which means we can go ahead and cross off B and C. Next, our second largest angle would be T, which means our second largest side is UV, and then our largest across from the largest angle would be UT. That leaves us with A as our answer. The last theorem is the triangle inequality theorem. The triangle inequality theorem allows us to look at the relationship of any two sides and the third side. Now, if I think about two sides here being set at 5 and 8, now this was the opening problem, notice that I can fold it around eventually so that this third side has to be about 3 if I get it that small, because 8 and 5, if they're coming together there, it has to be at least 3, a length of 3 in order to meet over there. Now I can get longer than that, but I can't get any closer than 3. If it is exactly 3, notice I don't really have a triangle there because it's actually on the segment. If I open it up the other way, making it longer, if I add 5 and 8, that would give me 13. But if I'm getting 13, it's a segment, not a triangle. To get a triangle, I have to be a little bit smaller than 13. So if my sides are adding up to something that is smaller than my third side, then there's no way that those sides can come together. So this is our triangle inequality theorem. We're making sure that two sides always add up to be bigger than the other side there. And so technically they're checking each pair of sides with the third side. Okay, so here's a problem where they're using that. Can a side have the lengths given? So they're going to start by adding each one of those. So maybe starting with 3 plus 7 is bigger than 8. Then they also checked that 7 plus 8 is bigger than 3. And 8 plus 3, is it bigger than 7? And all of those are working, 10 greater than 8, 15 greater than 3, 11 greater than 7. And since it satisfies all of those, then yes, it could have a triangle that fits that. Now the third one here, if we just start with 5 and 10, we see that it's not greater than 15, it's actually equal, and so this cannot make a triangle. Now notice in these, really all we need to check are the two shortest sides. If the two shortest sides, if I can add those up, and they're greater than the third side, then it would work. Now, so that one does not work. It's not long enough to have a third side of 9. This one here, if I take my two shortest sides, 4 plus 6, and compare it to 9, I'm getting 10 is greater than 9, and that one fits. Now in these, and according to our theorem, we should check the other ones, but if the two smaller ones are greater than the largest side, then obviously the other ones will work also. So it's enough just to compare the two shortest sides with the longest side. Another kind of problem will ask us to find possible side lengths. So they'll give us two lengths, 5 and 8, and ask what is the range of possible values for the third side. Now one way to think about this, rather than using all of those inequalities, just to think, well, if it's the shortest I could be, would be if I put them together coming like this, how long could that third side be? And we can see from this picture that if I subtract 8 minus 5, that would give me 3. So my third side there would have to be greater than 3 in order to make a triangle. If I go around the other way, if I connect them the longer way, the longest this could be would be adding those 8 plus 5, which gives me 13. If I'm longer than 13, it's going to be too long. I can't get a triangle. So putting those two things together, it has to be bigger than 3 and it has to be less than 13. We can say that 3 is less than x, which is less than 13, just to make sure our units are correct.